I was quite surprised at how simple this is. Turns out to be associated with essentially the density of updating activity in the
Right.
network. And then what happens is that that density of updating activity affects the kind of these shortest paths and produces the Einstein equations, which give you gravity and so on.
So that
So that's the story in
density,
space-time.
so is that to do with, is that information? Is that the amount of sort of transformational changes that are going on with a given system?
Well, I don't know. I mean, come on, think about it that way. I mean, it's it has to do with what, you have the state of the system, and you're asking, you're saying, well, yes, you change the system to another state. I guess one could say, I mean, in can one think of it as a rate of I think it's a bit of a slippery concept, but I think the uh I suppose you could, it is in a sense a rate of processing of the state of the system and how it changes.
Mm,
It's kind of how much change is happening in the system.
mm,
Um, I'm Here's why I'm hesitating. The problem is that what one means by quotes information is quite slippery. That is to say, this is, um, you could say, well, how much information is there really in the universe? Well, for example, in Rule 30, I can just tell you it's Rule 30, it starts from one black cell. Then I generate this giant thing. And the question is there more information in that giant thing than there was in me telling you it's Rule 30 and it has that simple initial condition? Or in the case of pi, I can say it's pi. But then when you actually get the digits generated, it's sort of an infinite sequence of things that seem random to you unless you know that it's pi.
mm.
And so there's sort of a whole question about when people talk about, information theory and things like this, what they're usually thinking about implicitly is something where the way that you can sort of grind down the signal that you get is very limited. You're saying, oh, I'm just going to break it into blocks and I'm going to use some kind of code that is sort of a very simple, well-defined code. And
Mm.
that's kind of what gets meant operationally by amount of information, but it's not, in some sense, the real amount of information. So it gets
Mm.
kind of tangled. I mean, the thing that
This reminds me of your thoughts on observer, the observer problem. There's a dotted line from here to that, isn't there? I think, and that's
yes, there is.
that
Yes, there
absolutely
is.
fascinated me because that's kind of one of the biggest challenges of science in a way, isn't it? To somehow sort of peer around the headset, as Donald Hoffman would sort of put it, to somehow bridge that gap. And it sounds like you're onto something with this. Would you be
Well,
able to
I think,
talk
I
us
mean,
through that?
okay, so the main issue is, uh, in the end, what matters to us about our experience of the world is what our kind of internal perception of what's going on is. And, you know, there may be lots of atoms jumping around and there may be lots of pixels on the screen, but we only notice certain coarse features of that. And turns out the laws of physics that we have critically depend on that fact.
Mm.
So the most obvious example of this is the second law of thermodynamics, law of entropy increase, the thing that kind of was one of my first sort of big interests I was mentioning before in physics, of kind of how do things go from being very regular to seeming very random,
Mm.
even though at a microscopic level, the laws of physics are reversible. So if you knew the position of every molecule, you could just reverse the movie strip and get back to where you started from.
Mm.
But that's not our experience of the world. And so that's a case where the way we are as observers critically affects our experience of the world. If we were observers who readily could work out all the details of how all these molecules are interacting, we would just say, well, there's just a bunch of molecules that are interacting in some way. We wouldn't say,
Mm.
oh, the second law of thermodynamics is happening, and we go from this very regular initial state to this random heat. We'd
Mm.
just be saying the molecules are doing this or that thing. But it's because we are observers who have this kind of computational boundedness that we just have to say, when we're confronted with a system that has, well, for example, computational irreducibility, we just have to say, we don't know what's going on. it looks kind of random to us. And so we build our experience of the world and our laws of physics on the basis of the way that we are as observers. And so the way that this gets sort of really, as far as I'm concerned, sort of super interesting. Actually, there are two more steps worth saying, because otherwise it's kind of hard to understand what's going on. So we're talking about quantum mechanics. I was talking about how, there are many different paths of history that you can produce. And the way to sort of think about things is the universe has these different paths of history which branch and merge and so on. And just like we are observers of a gas, for example, on a large scale compared to molecules, so we are also observers of the universe on a large scale compared to all these microscopic paths of history. So a kind of a weird thing is that our minds, like the rest of the universe, are branching and merging and so on. So sort of the story of what has to happen in quantum mechanics is a story of how does a branching brain perceive a branching universe. And one of the things that happens is this kind of, you can think about all these different branches of history, and they're all related to each other. So two branches of history we can think of as very close together if they share a common ancestor, if they both came from the same previous state and then through, let's say, one recent branch. And so you can kind of map out all these paths of history in what we call branchial space, the space of quantum branches. And that branchial space is not physical space. It's not space where we move things around in the ordinary way. It's a different kind of abstract space. But it turns out there are laws of motion in branchial space as there are in physical space. And essentially what happens is, we don't know all the details of this, but the qualitative story is the presence of activity in branchial space is associated with energy, as the presence of activity in physical space is associated with energy. And in the end, that presence of that energy causes a deflection of paths in branchial space. And it turns out that deflection of paths gives one the path integral of quantum mechanics. So the kind of the super cool thing is that what is the Einstein equations in physical space, in branchial space is the Feynman path integral. So in other words, the origin of gravity and of quantum mechanics, it's the same underlying conceptual